Welcome to Empowered Learning. This is the second video about the dot product operation for vectors. In the part one video, we went over all of the theory, concepts, applications of how the dot product could be used. That also included the derivation of the dot product, motivation from it, where it comes from. And we also defined what it meant to talk about the projection of some vector onto another vector. So we went over all of that in the part one video. If you're wanting to understand on a deeper level what the dot product is all about and why we even have this particular special vector multiplication operation, please check out that video. If you're more concerned with just seeing how the examples work and you're already sort of familiar with how the dot product works, then you want to go ahead and watch this video now. So what we're going to be doing here for example number one is we're basically going to be taking two vectors, v and u, and our goal is to eventually end up being able to calculate the projection of a vector u onto another vector v here. I need to put that there. So this problem asks us to basically provide all the sub calculations that we need to do in order to eventually end up with this outcome. Okay. And so we're going to do each example in order here. So the first thing I'm going to do to make life a little easier for myself is, even though I have this in the IJK form, I'm going to go ahead and write this in abbreviated component form just to make life a little bit more simple. Okay. So I'm going to write v and u accordingly. Okay. All right. So now that I have that, the first thing that I need to do is figure out what is going to be v dot u. And to do that, I just need to multiply the components of the first components of each vector together times the second components of each vector together times the third component. Of course, if I do that, I'll get 3/5 times 5 for the first two, the product of the first two, 0 times 12 for the second two, and 4/5 times 0 for the third. And of course, these last two terms end up being 0, and 3/5 times 5 is just 3. So we see that v dot u just ends up being 3. Next, we need to figure out the magnitude of v and the magnitude of u. So we're asked to do that here. So the magnitude of v is just going to be the square root of v1 squared plus v2 squared plus v3 squared. And of course, our v1 here is going to be 3/5. So that's just going to be 3/5 squared plus v2, which is 0 squared, plus v3, which is 4/5 squared. And if we work that out, well, we get 9 over 25 plus 16 over 25, which ends up being square root of 25 over 25, which is just 1. Okay, so we see that v in of itself is a unit vector. Okay, if we figure out the magnitude of u, that's just going to be square root of u1 squared plus u2 squared plus u3 squared. Of course, we have 5 squared here plus 12 squared here plus 0 squared. And this will just be 25 plus 144, which ends up being square root of 169, which is 13. So again, here we are just being asked to do all these calculations here. Now, again, the reason for that, and I'm going to switch colors here for just a second, is that our main goal is to be able to calculate the projection of some vector u onto a vector v here, okay? And we know that one way that we could calculate that is to say u dot v over the magnitude of v squared, all that multiplied by the vector v, okay? Now, of course, what we're seeing here, the scalar component also can be written this way. So we got all that, and then times a vector v. So that's essentially what we're working toward. So we could, so we can get our final result. So now that we have what v dot u is and the magnitude of u and v, the next thing that we're asked to do is find the cosine of the angle in between v and u. Of course, we know cosine of theta. This ends up just being, in this case, v dot u, or we could also say u dot v. And this would be over the magnitude of, over the product of the magnitude of both of these. Okay. So we already have our value for v dot u, which is 3. We have the value of magnitude of v, value of magnitude of u. So we see that that's just 3 over 13. And so now that we have all of that, we can now calculate the scalar component. So this is going to be the scalar component of u in direction of v. And I'm writing this out this time, but I won't write this out anymore. And we know simplistically this could just be the magnitude of u times cosine of theta. And of course, the magnitude of vector u is 13. Cosine of theta, we know, is 3 over 13. So that result, after the 13 is reduced to 1, just ends up being 3. And so now finally, what we have is the projection of vector u onto a vector v. Of course, and yes, I forgot to write something up here. Whenever we do this, if we rewrite this, let me make sure I make this correction here. If we rewrite the scalar component this way, I'll also have to divide this by the magnitude here, because this is the actual portion from the vector, the actual portion of the magnitude from the vector u that's being transferred on to v. But we also have to account for the fact that we're going in the direction of v, so we have to have the unit vector there. Okay. So saying all that to say here that if I'm going to do calculate the projection of u onto v, then I could do it this way. Let's put this here like that. Could do it like this. But since we already know what cosine theta is, we're going to rewrite it this way. Okay. So here I already know what the magnitude of u is 13. And magnitude of u cosine theta here just ends up being 3. So I already have that business there. We know that the magnitude of vector v is just 1. So this is really just 3 times the vector v. And the vector v, if you remember, was 3/5 in I direction plus 4/5 in the k direction. So you could write it like this. And if you want to, you can kind of multiply into 3 if you like. Not necessary here, but you can do it. And so either one of these two would be our final result. And so those vectors in either form will actually just end up being the new vector that results when the vector u acts upon the vector v, okay, in the direction of vector v at a particular instant in time. So that is what that projection actually represents. All right, so let's look at our next example. All right, so for our next example, it'll pretty much be the same thing. Now we actually have an x, y, and z component for all 3 of our vectors, so that's why I'm doing this one. And we could look at this as 2, 10, negative 11, if we look at it in component vector form. And this would be 2, 2, 1 in component vector form. So again, our goal is to be able to calculate the projection of a vector u onto a vector v, and we are going to calculate it this way. Okay, I'll calculate it like that. And let me clean that up here. Okay, so of course, let's get this. So we need to figure out what v dot u is going to be first. Okay, and if you figure out what v dot u is, it's just going to be the product of the light components. So 2 times 2 is going to be 4, plus 10 times 2 is going to be 20, plus negative 11 times 1 is going to be minus 11. So we'll do minus 11 here. And if we do that, that's going to end up being 13 once that's all worked out. Of course, the next thing that we need to do is figure out what the magnitude of v and u will be. So of course, the magnitude of v will just be 2 squared plus 10 squared plus negative 11 squared. This will be 4 plus 100 plus 121. And that's literally 104 plus 121, which is 225. And the square root of 225 is 15. Do the same thing for the vector u. We'll have square root of 2 squared plus 2 squared again, plus 1 squared. And that's just going to be 4 plus 1, which is 9. And square root of 9 is 3. So now that we know what the magnitude of both u and v are, we can now just go and figure out what cosine of theta is, which is going to be v dot u over the magnitude of v, product of the magnitude of v and u. So we know that v dot u is 13. We know that the magnitude of v is going to be 15, and the magnitude of u is going to be 3. So this ends up being 13 over 45. Okay. And so now, if we want that scalar component of u in the direction of v, scalar component, that's just going to be the magnitude of u cosine theta. And that will just be 3 times 13 over 45. And of course, we know that 45 is just 15 times 3. So if we reduce this, this would just be 15. So this would just be 13 over 15 here. And then lastly, what we need to do is actually calculate the projection of vector u onto the vector v. And this will just be absolute value of, or sorry, the magnitude of the vector u cosine of theta. Let me not do the multiplication with a dot there. Let's just do it like this, and then we'll have the vector v divided by its magnitude, or have that unit vector. So we already know that magnitude of u cosine of theta, that's just 13 over 15. For our vector v here, we know that its magnitude is going to be 15. So one of the things I could do here is I could say, since this is going to be the same as 1 divided by the magnitude, scalar multiplication times the vector v, it could look like this. And of course, 15 times 15 is just 15 squared. So I'm just going to leave it like that. Oops, let's undo that. And of course, 15 squared is just going to be 225. So I'm just going to go ahead and write that number in. And all we got to do now is deal with v. And of course, v is this vector here. So I'm just going to go ahead and write that in. And so this would be 2 in the I direction plus 10 in the j direction minus 11 in the k direction. And that would be what the projection of our vector u onto v would actually be. All right, for our last example, I've already worked this out, but you'll see that it's pretty much the same flow. The only thing that's different now is that we're dealing with a lot of square roots. So doing some of the calculations may be a little tricky, but it's pretty much the same flavor as what we've done before. So of course, we see that v and vectors v and u are already given in component form. So that makes that eliminates one step. And so here, of course, if we do v dot u, we just multiply the two components, first components together plus 2 second components together. And we see in this case that we end up getting a positive 1/6 for that. We find the magnitude of v and u accordingly just by doing the square of each component, adding it, and then taking the square root of that. We find cosine of theta, which is just going to be v dot u divided by the product of the magnitudes of v and u. And we see we get 1/5 there. The scalar component, since we know what cosine of that angle is just going to be the magnitude of u times cosine of theta, which ends up being 1 divided by square root of 30. Of course, for those of you that are kind of particular about having irrationals in the denominator, you could rewrite it like this: square root of 30 divided by 30. Okay. And then, of course, the projection is just going to be the scalar component times the unit vector for v. Okay. And so that's what this says here: scalar component of the projection times the unit vector of v. And if we do all of that, we see that we end up getting, if I scroll down a little bit more here, we end up getting 1/5 times the vector v. And of course, if we write that in the unit vector format with the I, J, and the K, then it ends up just looking like this. Okay, so for our second example, we're given a vector u and a vector v, and we just want to find the angle in between each vector. Angle in between the two vectors. Okay. So again, I've taken the vector u and v in this case, since I've already worked this one out, and I've put it in component form just to make it a little bit easier to look at. You don't necessarily have to do that step. I just do it because in my mind it looks better to put it in component form than leaving it in the unit vector form with the I, J's, and the K's. Okay. So once I have this in component form for both vectors u and v, then of course I just use this formula here, do the dot product, which is just going to be taking like components and multiplying them together and then adding the result. We see that when we do that in a numerator, we end up getting 10. And of course, we take the magnitude of u and the magnitude of v, just kind of like how we did in example 1. And we see that we end up getting 3 and 5 respectively. Of course, reduce that fraction and we end up getting 2/3. And so now only thing we have to do is take the arc cosine or cosine inverse of 2/3, and that ends up being 0.84 of a radian, which tells us that our angle is going to be in quadrant 1. So in between 0 and 90 degrees if we were thinking that. Okay. All right, so example 2, we will work out together. So for example 2, our vector u here we can express as 1, comma square root of 2, comma negative square root of 2. And v will be -1, 1, 1. Okay. So to find the angle in between the two vectors, we would just do u dot v, cosine inverse of u dot v, times the product of the magnitudes of each. All right, so for the dot product, we would take 1 times a -1, which would be -1, plus square root of 2 times 1, which would be square root of 2, plus negative square root of 2 times 1 would be a negative square root of 2. Okay. Now the magnitude of u, that would be square root of 1 squared plus square root of 2 squared plus negative square root of 2 squared. And of course, magnitude of v would just be -1 squared plus 1 squared plus another 1 squared. Need to make that look a little better. Okay. So now all that's done, we can do our calculations here. Cosine inverse of course, this square root of 2 and that minus square root of 2 cancel to 0. So we just have a -1 here. Have square root of 1 plus 2 plus 2. So 1 plus 2 plus 2 is going to be 5. And here we have 1 plus 1 plus 1. So that'd be square root of 3. Which is just cosine inverse of -1 over square root of 15. And of course from here, we can just calculate what our final result would be. And let's make that 15 look a little bit better here. All right. And of course, if we calculate that, we would end up getting 1.83 radian. Okay. And this would end up being in quadrant 2. So an angle in between 90 and 180 degrees. All right, let's move to the next example. So for our third example, what we see here is that we have a simple application of what we were doing in example 2. So in example 2, we were just trying to find the angle in between two vectors. Here what we have is an oblique triangle where we want to find out what is the measures of angles alpha, beta, and theta. And if we look at the sides of our oblique triangle as directed line segments, then we can treat each side of our oblique triangle as a vector. Okay, so because of that, all we really have to do here is figure out, well, what is going to be what is vector AB? What is going to be vector AC? What is going to be vector CB? Okay, and I'm saying it like this because anytime, if we're going to find alpha, we need to find the angle in between these two vectors where both vectors start at the same point. Okay, so vector AB and vector AC would be for alpha. For vector C, I would have vector CB and vector CA. And for theta, I would have to have vector BA and vector BC. Okay. And note that vector AB and vector BA are just the same vector, just in the opposite direction. So vector BA is just going to be the negative of vector AB. Vector CA is going to be the negative of vector AC. And vector CB is going to be the negative of vector BC. Okay. So in knowing that, if we just find these vectors, then we can just use that in the formula for cosine of an angle is going to be the dot product of the two vectors divided by the product of the magnitude of both of those, and we can find out what the angles are. So I've already done some of the work here. So we see here that to find out vector AB, I'm just taking the difference in between the associated terminal point of B in its components to the initial point A. So if I look here, I see that for vector AB, I have 2 minus a negative 1, which is 3, and 1 minus 0, which is 1. And so that's how I end up getting this vector here. Now, all the other vectors that I come up with, I'm doing the same way, taking the final point and subtracting all the corresponding like components of the initial point. And so that's how I get all of these vectors here. Okay. Now, of course, note 1 says that we must have both vectors start at the same point when using the formula that we're going to use here, which is this cosine of whatever angle it's going to be, is going to be u dot v over the product of the magnitudes of u and v. Okay. So whatever that angle is, of course, both u and v are going to have to start at the same point in order for us to properly use this particular formula. And so note 3, of course, is just calculating the magnitudes of all 6 of the vectors that we need. And if you remember, vector AB is the same as vector BA, but just in the opposite direction. Magnitude wise, they would be the same. So that's why I only needed to calculate 3 magnitudes here. So if you're following along, you may want to take note of these magnitudes here. Pause your video, write that down. So you may want to do that here. Also for the actual directed line segments, aka vectors themselves. You may want to write these down so that you have those, or try to calculate them on your own, see if you get the same thing. And then after that, we can go and run through these examples now that we actually have all the information that we need. So if we're trying to find the angle for alpha, then of course we would say cosine of alpha is going to be the vector AB dotted with the vector AC all over the magnitude of vectors AB and vector AC being multiplied times each other. Okay. Now, we know here that for our vector AB, we have component vector 3, 1. For vector AC, we have the component vector 2, negative 2. And of course, for the magnitude of AB, we already have square root of 10. And for vector AC, we have basically square root of 8, but I'm going to rewrite it as 2 times the square root of 2. Okay. All right, and so in doing this, our denominator here, if we split up this square root of 10 as square root of 2, square root of 5, then we're going to have 2 times square root of 2 times square root of 2, and that ends up being 4 times square root of 5. For our dot product, we would have 3 times 2, which is 6, plus 1 times a negative 2, which is minus 2. And of course, all of that is just 4. And so this just lends us to say that 1 divided by square root of 5 is what cosine of alpha would be. So therefore, alpha would just be cosine inverse of 1 divided by square root of 5. And since 1 divided by square root of 5 is positive, we know that this angle is going to be in quadrant 1. In terms of radians, we would get 1.107 radians. Okay. In degrees, this would be roughly 63.43 degrees. Okay. All right, so let's look at the next example. I'm going to do the same thing, just a different angle now. And of course here for beta, we're now starting at this point 1, negative 2, and we'll be looking at the vectors, so vector CA and vector CB, okay? So for here, we would say cosine of beta is going to be, we're going to look at vectors CA dotted with vector CB all over the magnitude of both of these vectors and multiplying together. All right, so we know that vector CA is just negative 2, 2. Pen is starting to hang up here. And we'll dot that with vector CB, which is 1, 3. So for the magnitude of vector CA, we see that that's just going to be 2 times the square root of 2. And vector CB, its magnitude is square root of 10. Okay, so pretty much what we had up here in this first example. Okay. So because of that, we already know that the denominator here is just going to end up being 4 times square root of 5 again. Our numerator is going to be the dot product of these two vectors. So negative 2 times a positive 1 will be minus 2. plus 2 times 3 is going to be 6. That's just going to be 4 over 4 times square root of 5. So we essentially have the same answer again. Okay. So here we know beta is going to be equal to alpha in this case, because again, we're going to end up with the same thing here, which is going to be 1.107 radians. And I probably need to put radians here. Or 63.43 degrees. All right, so for our last example, we are trying to find the angle theta. And if we go back up to the top here, we know for our angle theta, we're looking at the vector BA. So start at B, end at A, and the vector BC. Start at B, end at C. So we come down here. Cosine of theta is going to be equal to, we start off with, let's see, vector BA dotted with vector BC, and then divided by the magnitude of both of these vectors multiplied together. Of course, vector BA is just going to be -3, -1. And we dot that with vector BC, which is -1, -3. And of course, the magnitude of BA is the same as it was for AB, which is square root of 10. And the magnitude for BC is the same as it was for CB, which is also square root of 10. Okay. So we know that our denominator here is just going to be 10, because square root of 10 times itself is just going to be 10. The numerator, when we dot these two vectors together, will have -3 times -1, which is a +3, plus -1 times a -3 is a +3. And so from there, we see that that just ends up being 6 over 10, which should be the same as 3 over 5. And so this implies that our theta would be cosine inverse of 3 over 5. And again, since this 3 over 5 is positive, and I'm saying that because if we were looking at this way, cosine of theta is equal to 3/5 or 0.6. Since 3 over 5 is positive, we know that our angle theta here is going to be in between 0 and 90 degrees. And if we were to actually put that in our calculator and figure it out, this would be roughly 0.93 radians. In degrees, it would be roughly 53.13 degrees. So go ahead and write that here. Okay. All right, so that concludes this example. We'll go ahead and move on to example number 4 now. All right, so example number 4 says that we have a water main that is to be constructed, and we know that we have a 15% grade in the north direction and a 12.5% grade in the east direction. And what we want to do is figure out what that angle theta is required in the water main for the turn from north to east. Okay. Now, when we first read this problem, you may not be familiar with all of the terminology that's in it. And because of that, that makes this problem a little tough to get started. But I'll go through what all this stuff means so that if you're not familiar with this sort of terminology or jargon, you'll kind of understand what's going on here. Okay. So water main, we just basically have, these large pipes that's going to carry water in it. Okay. And of course, we want to transport water from one place to another. And at times, we're going to have to, make some turns depending upon where we're trying to get the water to. Okay. So when this problem talks about a grade, what it is talking about is another way of saying that is maybe the pitch at which this pipe is being installed as it's being laid to get to wherever it's trying to get to. Okay. So in short, when you think of the word grade, what you need to think of is slope, because what you're essentially trying to do in a very succinct way is communicate what is going to be the rise over to the run, depending upon what direction you're going in. Okay. So for instance, when this says that we have a 15% grade in the north direction. Okay. So what's implied here is that you're trying to compare the rise, meaning how much you're going up vertically versus how much you're going across horizontally in the north direction. Okay. So because of that, what a 15% grade would actually end up being here. And I'm just going to use feet as the units here, even though it doesn't say that. You think of this as rise over run. And one way you can interpret this is to say, all right, so for every 15 feet I go up vertically, okay, I'm going to run horizontally 100 feet. That's one way that you can say that. Okay. Now, of course, if we put this in vector notation, going in a vertical direction is like going in the K direction. Okay. If I'm going horizontally, and if it's in the north, and I'm assuming that this north direction here, according to how this is drawn, I'm going to assume that's going to be in the X direction. Then I'm going to say that I want 100 feet in the I direction here. Okay. So, of course, I could reduce that fraction, break it down until it's simplest terms, and I'll use that to be able to help me out here. But in general, that's what they mean by a grade. Okay. I'm going to do the other one here as well. So before I do that, I'm going to go ahead and set up my coordinate system so that when we do this grade and then translate that into actual vectors based upon points that we've defined on our coordinate system, all of this will make sense. Now, one of the keys to what we have to understand to be able to apply what we need to this problem is that we're trying to find the angle in between two essentially vectors here. Okay. So that means that those vectors have to start at the same point. And so what we're going to do here is assume that this point here is the origin. Okay. Meaning that it's going to be the point 0, 0, 0, since we're in 3 dimensions here. Okay. So in doing that, if this is going to be the origin, then what I'm drawing here is going to be the positive x-axis. And what I'm drawing here is going to be the positive y-axis. And let me move this over here. And what I'm drawing here is going to be the z-axis. Okay. Of course, what I'll do is I've already said that that's the origin, so I'll just write this as the point 0, 0, 0. Okay. So if we look at it that way, then not only do we know, not only do we have a coordinate system for us to be able to find points for where, for sole purposes of this example here, where our water main pipe starts and stops, we can also use those points to be able to define vectors. Okay. So now that we have this, let me go back and do this other grade here and interpret that. And I'm going to simplify them both later, but I'm just going to keep them the way that they are now. So if I have a 12.5% grade here, then, and this is in the east direction, notice that the east direction is parallel to the y-axis here. So this is still going to be rise over run, but in this case, the run is going to be in the j direction, whereas the rise will be in the k direction. And we know by definition, percent is per 100. So this would be 12.5, let's say feet per 100 feet. Okay. And again, I'm just using feet to, as a means of having a unit there. We don't necessarily need the unit for this. All right. So now that we have that, if I was to simplify this fraction here, I know that 15 and 100 both have a common factor of 5. So 5 goes into 15 3 times, 5 goes into 20, 5 goes into 100 20 times. So we would have fraction of 3 over 20. This would be 3 in the k direction, 20 in the I. Okay. 12.5 divided by 100. If we multiplied 12.5 times 8, we would end up getting 100. So we know here for, I take 100 divided by 12.5, we're just going to end up getting 8. So we're going to have 1 in the k direction for every 8 in the j direction. Okay. Now, how does this translate to what we're going to do as far as doing this coordinate system and trying to find these points? Okay. Well, here, and I'm going to change colors. If I want to find out what this particular point is here, if this is the origin, notice I got to go down first and then across in the positive x direction. Okay. So I got to go down in the z direction and then over in the positive x direction. So what this tells me, since my grade is 15%, this tells me if I go down 3 feet, then it means I have to go across 20 feet. Okay. And if I look at that in terms of a point here, the x coordinate for this point will be 20. The y coordinate for this point, since y goes in this direction, is 0. And the z coordinate, since I had to go down from the origin, would be a -3. So that would be what that point is. Okay. Similarly, if I wanted to find this point, what this 12.5% grade is telling me is that to get from the origin to this point, I had to go due east. If I look at this, I go due east 8 feet for every 1 foot I go up vertically in the z direction. So here, this point will end up being 0 in the x direction. It'll be 8 in the y direction, and it'll be 1 in the z direction. Okay. So because of that, what we see here is that if I wanted to now, let's say, name these vectors here, and let's say this is a point A, this is a point B, and let's say this is point C here. Okay. And actually, I'm gonna switch these up here. Yep. So I'd like A to be my origin there. So let's say A is the origin, and then we let this that point be B, and this other one be C. Then what we see here is that we have a vector AB and a vector AC that we can consider. And if we can find out what those actual vectors are in component form, we could actually use that to be able to find the angle in between. We can find the angle in between these two water main pipes here. Okay. Now, because of the fact that A is the origin, the points that we found here are actually going to be, we can actually use the same thing to come up with the components for the component form of the vectors. So what I'm trying to get at here is that my vector AB could be expressed as 20, 0, minus 3. And of course, these little symbols up here I'm doing on the end that look like less than and greater than signs, I have to write it like that if I'm doing the component form of a vector. I can't write it like this. So it has to be written like this for it to be interpreted as a component vector. If you write it like this, it's going to be interpreted as a point. And that's not what we're doing here. We're considering vectors, not points. Okay. All right, so for vector AC, we'd have 0, 8, 1, like that. So now that we have this, we know that in order to find the angle in between these two vectors here, all we have to do is figure out what cosine of theta of vector AB dot vector AC over the magnitude of both vectors AB and AC multiplied together. Okay, so now that we have this business here, we also know that if I dotted these two vectors together, I would have 20 times 0, which is 0, plus 0 times 8, which is 0, plus negative 3 times 1, which would be a minus 3. Okay, so my result here would be a minus 3. So when I calculate that, I would have a minus 3 there. Now, the magnitude of vector AB, that's just going to be the square root of 20 squared plus 0 squared plus minus 3 squared. Okay, and this will end up being the square root of 409. If I do the same thing with vector AC, this will be square root of 0 squared plus 8 squared plus 1 squared. And this would end up being square root of 65 whenever I work all that out. So here, this tells me that I have square root of 409 here times square root of 65 here. And so now, with all that being done, then of course, this angle here is just going to be cosine inverse of this quantity here. And this is 409, not 404. Okay. And if you work that out, put it in your calculator, whatnot, you'll end up getting like 1.59 radians, roughly. In degrees, that would be about 91.1 degrees. Okay. And so that would be your final answer for this. Okay. Now, if you're thinking about this, in reality here, we probably wouldn't want that angle to be so close to being a right angle. Just because the way that fluids flow, if you make them make a sharp turn like that, they're not going to be able to flow as fast as if you relax the angle some. Okay. So in other words, if the angle was more along the lines of, let's say, 120, degrees, something like that, then of course it would be a little bit better. Okay. But again, this is just an example. The main thing was to try to communicate to you how to work this problem, to figure out when they're talking about 15% and 12.5% grades, what does that actually mean, and apply that to trying to find this angle by using what we know about the dot product. Okay. All right, so let's move on to our final example. All right, so for our final example, I've already worked this one out, but I chose this example here because I wanted to showcase something that I actually talked about in the video on the basics of vectors. Okay, the one that if you're watching these videos in succession, you should be watching. You should have watched that one before you watched this one. Okay, so the main thing here is that notice that this question talks about the direction angles of alpha, beta, and gamma for a vector in 3D space. Okay, whereas components are in terms of the I, J, and K unit vectors, which is just unit vectors for the X, Y, and Z axes respectively. Okay, so the point here is that you see how we have alpha, beta, and gamma defined. Okay, alpha is the angle in between the vector v itself and the positive x-axis. Beta is the angle in between the vector v itself and the positive y-axis. And of course, gamma is going to be the angle in between the vector v itself and the positive z-axis. And of course, the range that those angles could possibly be is anywhere in between 0 to pi in radians. In degrees, that'd be 0 to 180. And again, the reason for that is, if we remember, the whole notion of a dot product came from trying to be able to figure out what is going to be the angle in between two sides of an oblique triangle. And of course, angles in a triangle have to add up to be 180 degrees. So we can't go over that. Okay. So the point here for this particular problem is that if I wanted to find out what is going to be the z component in this vector, in other words, if I wanted to find out what is going to be that value c there are several different ways for me to do that. Okay, several different ways for me to do that. I could, if I know what the magnitude of v is, and I know what gamma is, then I could find out what that component is with respect to the z-axis. If I knew what beta was and the magnitude of v, I could find that out, find out what that value c is in terms of the positive y-axis, so on and so forth. Okay, so there's not one standard way to do it, and that was one of the things that I mentioned. Okay, so to just summarize my point here, example 5 is going to be an example of the reason why, if we wanted a scalar component, I called it v of z in the video that I did. In this current problem, it would be that scalar value c. Of course, I wrote it like this, but in this problem, it would be c. We don't have a standard way of doing it, like how we do with the x and y components, and of course their corresponding magnitudes. We have a standard way of doing that, but we don't have one for trying to find the scalar or real number part of the z components. Okay, so that's why I refrained from doing that in that video, and that's the purpose of showing you this example here. All right, so the first thing that we want to do here is to show that if I do cosine of alpha, cosine of beta, cosine of gamma, that I'm going to get this result of A divided by the magnitude of V. Beta, cosine of beta is going to be B divided by the magnitude of V. Cosine of gamma is going to be C divided by the magnitude of V. And of course, if I add the squares of all of those cosines together, I'm going to get 1. Okay. Now, to start this off, I'm going to need to be able to define these sides here that I'm looking at as vectors. And so I left off some points here. So I'm saying here that P, Q, and R are actual points on this graph. But of course, we also have S and we have T as well. So I'm going to go ahead and write that in here. So we're going to have S and we have T as well. All these are points. And of course, the A, B, and C, they're scalars or real numbers. Okay. Now, according to what I have here, and knowing that this vector v starts at the origin, I know that my points for S, P, Q, R, and T are accordant. Okay. So now that we know what these points are, I can actually find the angle alpha, beta, and gamma by translating the sides that kind of go out to these points here, whether it's P, Q, R, or T, as vectors. So for instance, for alpha, I can look at this particular vector here. So the vector going SP, and this vector here, ST, okay? And of course, to do that, I can find out what alpha is. So if I dot the vector SP with vector ST, then of course, the vector, let's see, the vector SP is just basically going to be, if I look at this, it's just going to be A0, 0. That's basically what that one looks like. And the vector ST, that's just going to be A, B, C. Okay. And if I dot those together, notice I got A times A plus 0 times B plus 0 times C. And of course, it ends up being A squared in the numerator. In the denominator, I know that the magnitude of SP, if we look here, the magnitude of that, if I did square root of A squared plus 0 squared plus 0 squared, that's just going to be A. And if I did the same thing with the magnitude of ST, okay, that's just going to be square root of A squared plus B squared plus C squared, okay? And of course, this A and A squared here, A squared divided by A is just going to be A. And of course, if you remember down here, square root of A squared plus B squared plus C squared is just the magnitude of V itself, okay? So I see all that, and I have verified this. If I do the same sort of thing with both beta and gamma and trying to find that, you'll see that from the work here that cosine of beta is going to be equal to B divided by the magnitude of V, and cosine of gamma is going to end up being C divided by the magnitude of V. And then, of course, from there, what I could do is I can square all of these, add them together, and I should see that I end up getting 1. So on the next page here, the summary of the result, cosine of alpha, cosine of beta, cosine of gamma is going to be A, B, and C, all those divided by the magnitude of V. If you square those, in the denominator, it gets rid of the square root sign. In the numerator, it just squares the A, B, and C respectively. And of course, if we add all these together here, we'll just have A squared plus B squared plus C squared divided by the same thing. And that ends up giving you 1. Okay. Now, part B just basically says if our vector V in itself is a unit vector, then the values or the letters A, B, and C are actually going to constitute the direction of cosines. Okay. Now, to kind of back up a second here, you got to remember that our vector V was defined as A going in the I direction plus B going in the J direction plus C going in the K direction. Okay. So what we're saying here is that if our vector V is a unit vector, meaning that the magnitude of it is 1, then basically what that means is that the square root of A squared plus B squared plus C squared, all that's just going to be 1. Okay. And because of that, we see that we're just taking A, B, and C for our cosine, alpha, beta, and gammas and just dividing it by 1. And of course, when that's the case, then of course we see that the direction cosines just end up being the coefficients themselves. Okay. All right. So this gives you some examples of how we actually use the dot product to be able to do various things. The next video that I'm going to do will be about cross products, and you're actually going to see how the dot product kind of sneaks its way into there to do some of the things that we need to do there. But the main thing I want you to remember about the dot product is that the purpose of the dot product is to handle the phenomenon that happens when two vectors interact in a way to where we may interpret it as multiplying the two vectors together, but the dot product just captures the magnitude perspective or the magnitude aspects of what happens when two vectors interact that way, okay? Of course, the cross product will be what happens with the rotational aspects of what happens when two vectors interact with each other this way. And so that's what we'll talk about in that video. Hope to see you there.